Welcome to the third part of 11th Physics, chapter Mechanical Properties of Solids. In this part, you will learn about the stress-strain relationship graph. In the last part, we have studied about the Young's modulus of elasticity. Let's solve a numerical based on that concept first. It's your NCERT example 9.1. A structural steel rod has a radius of 10 millimeter and a length of 1 meter. 100 kilonewton force stretches it along its length, and you have to find out stress, elongation, and strain on the rod. It's given that Young's modulus of structural steel is 2.0 into 10 raised to power 11 Newton per meter square. We have already studied about the stress formula. Elongation means delta L, and strain, change in length upon original length. So by using all these three formula, just give a pause to the video and try to solve yourself. We know that stress is equals to force upon area, and area is pi r square. All the values are given to us. Just put in the this formula and you will get the stress. That comes out to be 3.18 into 10 raised to power 8 Newton per meter square after calculation. Elongation means change in length. Delta L will be equals to F by A into L divided by Y by using the formula of Young's modulus of elasticity. And by putting all the values in and solving it, you will get 1.59 millimeter. And the strain, you know that it is the ratio of the change in length upon original length. And it is 1.59 into 10 raised to power minus 3, or in the terms of percentage, it is 0.16%. Stress-strain curve. The relation between the stress and strain for a given material under tensile strength can be found experimentally. In a standard test of tensile properties, a test cylinder or a wire is stretched by an applied force, and the fractional change in length and the applied force needed to cause the strain are recorded. And the applied force is gradually increased in steps, and the change in length is noted. And then a graph is plotted between the stress and strain produced as shown. Here is the variation at different steps of stress, and correspondingly the strain is drawn. The graph helps us to understand how a given material deforms with increasing loads. Within the elastic limit, the curve between O and A is a straight line. That means the stress is directly proportional to strain. And the Hooke's law is applicable to this region. In the region from A to B, stress and strain are not directly proportional. But still, the material regains to its original dimension after the force is removed. That means they exhibit elastic properties. And the point B in this curve is known as yield point, also known as elastic limit, which means till this point the material will be in elastic behavior, and the stress corresponding to the point B is known as yield strength of the material. The region between O and B is called elastic region. From point B to D, Again, the strain increases rapidly even for small changes in stress. And even if we remove the force, the material doesn't come to its original position. At this point, stress is zero, but strain is not zero. And the material undergoes plastic deformation. And the material is said to be permanent set, as shown in the graph. The point D on the graph is known as ultimate tensile strength of the material. From D to E, stress decreases even if strain increases. Finally, at point E, fracture occurs. This means the body breaks.